Welcome to this explainer. Today, we're diving into a pretty vital intersection: natural forces versus human engineering. The threat of extreme weather and major seismic events is an escalating reality across the globe. But against these severe natural hazards, we actually have a solid line of defense. We're talking about strict engineering codes and resilient infrastructure. Throughout this explainer, we'll explore the specific global standards and disaster-resistant construction techniques that are specifically designed to keep our communities standing when nature strikes. By examining the precise mechanics of how buildings survive, we can really understand the invisible armor protecting the spaces where we live, work, and park every single day. So this brings us to a fundamental question, right? Are our buildings actually engineered to survive these extreme natural forces? When we contrast the raw, completely unpredictable power of natural disasters with the highly calculated math of human engineering, we find that survival isn't just a matter of luck. No, the outcome entirely depends on the standards we choose to enforce before the disaster even occurs. Every single beam, bolt, and foundation represents a deliberate choice to resist the chaotic energy of the planet. To guide our analysis, we're going to follow a structured map of 4 core hazards. First, seismic safety. Second, wildfire resilience. Third, flood and coastal protection. Fourth, wind protection. And finally, number 5, we'll evaluate the economics of resilience to really understand the financial reality behind these standards. Section 1, Seismic Safety, Engineering for Earthquakes. We're starting our elemental approach with the Earth itself, focusing on exactly how our buildings perform during major seismic events. To truly grasp why these standards are so absolutely crucial, we only have to look at the devastating aftermath of the deadly earthquake in Venezuela. That damage exposed exactly what happens when strict code enforcement is lacking. Investigations there highlighted rushed construction and a total failure to adhere to global seismic standards. And it underscores a critical reality. Brilliant engineering design on paper means very little without rigorous oversight and mandatory public building audits, because without enforced codes, well, the ground shakes and entire communities are left utterly defenseless. Now, when engineers audit buildings, one of the primary vulnerabilities they hunt for is what's called a soft-story building. Picture a structure featuring a weak lower level. That's often an open parking garage or maybe a retail space with expansive glass windows. These lower levels lack the solid shear walls needed to resist lateral, side-to-side movement. That makes them highly vulnerable to just collapsing right onto their own footprints during an earthquake. Mitigating this specific structural weakness through targeted retrofitting is a major focus for risk reduction programs, like California's Earthquake Brace and Bolt initiative. Targeted retrofitting transforms these vulnerable structures into highly resilient ones, and the engineering solutions are actually quite practical. Foundation vaulting and cripple wall bracing physically anchor the wooden frame of a building directly to its concrete base. That prevents it from just sliding off during a violent tremor. For larger multifamily buildings, we use staged incremental rehabilitation that allows for vital structural upgrades without ever displacing the occupants. Plus, utilizing advanced tools like the Applied Technology Council's ATC 58 performance assessments allows building owners to accurately estimate potential damage, repair costs, and downtime. It basically transforms guesswork into highly informed engineering choices. And modern performance-based engineering scales way up to protect major public infrastructure too. Take Levi's Stadium in California. It was engineered using advanced buckling restrained braces. These essential components act essentially as giant structural shock absorbers. Instead of remaining rigid and brittle, they are specifically designed to yield and safely absorb seismic energy without buckling under the immense pressure. It's a prime example of how major public venues are engineered to safely withstand severe shaking and nearby earthquake swarms, protecting tens of thousands of people all at once. Section 2, Wildfire Resilience. The wildland-urban interface. Transitioning from earth to fire, we have to examine the specific engineered solutions required when neighborhoods border densely vegetated wildland areas. As suburban development expands deeper into natural landscapes, we really need to establish a critical piece of terminology: the wildland-urban interface, or WEI for short. These are the specific zones where human-made structures directly meet or intermingle with undeveloped wildland vegetation. Because these exact areas face exponentially elevated wildfire risks, strict regulations like California's updated 2026 building codes now mandate specialized, highly tested fire-resistant construction for any home built within them. The entire goal here is to create structures that can withstand the extreme conditions of their surrounding environment. The science of home hardening relies on a precise, multi-layered sequence of defense. It starts right at the top. First, installing Class A fire-resistant roofing is paramount to deflect falling embers. Second, Fitting ember-resistant vents ensures that airborne embers aren't sucked into the attic to cause internal ignition. And third, establishing a strict 5-foot non-combustible defensible zone immediately around the structure removes any fuel source right where the building meets the ground. It is a very systematic approach to denying fire the fuel it desperately needs. Additional WUI building upgrades include ignition-resistant siding, fire-rated windows that won't shatter from extreme radiant heat, and fire-resistant decking. It is important to note that it's rarely a sweeping wall of flame that destroys a house. It's actually a relentless blizzard of windblown embers. While no home is entirely fireproof, selecting these scientifically approved materials, combined with routine roof and gutter maintenance, drastically reduces the risk of ember ignition during a localized firestorm. Section 3. Flood and Coastal Protection, Managing Water. We turn now to water. In this section, we're evaluating how we elevate, armor, and adapt our structures against severe flooding and rising coastal threats. When you absolutely cannot completely avoid flood zones, building science offers two primary strategies. The first is wet floodproofing. This strategy intentionally allows floodwater to enter limited-use enclosures, like a crawl space or maybe an unfinished garage, to equalize hydrostatic pressure. Think about it. If you try to keep all the water out of a standard residential basement, the sheer weight of the outside water can actually push inward and snap the foundation walls. On the flip side, we have dry floodproofing. This utilizes specialized shields and sealants to keep water completely out. It's a much more expensive strategy, and it's frequently reserved for commercial and public buildings. So the truly crucial point here is that resilient building design cannot just stop at the front door. It has to encompass the wider community's lifeline infrastructure. For example, elevating and armoring electrical substations in floodplains is strictly required to maintain power during extreme 500-year storm events. If the power systems fail, even the most rigorously flood-proofed community is going to struggle to recover. Essential services like water pumps, communication networks, and emergency medical facilities, they all rely on an unbroken flow of electricity. Beyond basic floodproofing, critical mitigation strategies involve elevating structures well above base flood levels and utilizing breakaway walls below coastal buildings. This sounds totally counterintuitive, but it's brilliant engineering. You build walls designed to wash away harmlessly under wave pressure, rather than acting like a sail that pulls the entire house down. We also really have to emphasize nature-based solutions. Integrating wetlands and dunes directly into coastal planning acts as a natural sponge. It physically reduces flood depth and absorbs wave energy long before it ever hits a human structure. Section 4. Wind Protection, Fortifying the Envelope. Our final natural hazard is extreme wind. Whether we're talking about hurricanes or tornadoes, structural integrity during a high wind event relies entirely on the continuous connections of the building itself. Wind protection requires a heavily reinforced building envelope. A continuous load path physically ties the roof to the walls to the floors, and the floors to the foundation. Without this continuous connection, uplift forces can easily peel a home apart right from the top down. Properly braced garage doors and impact-resistant opening protection, like shutters, are absolutely vital. If a high-velocity wind breaches a large window or door, the sudden internal pressurization inflates the home like a balloon, and that can instantly blow the roof entirely off the building's frame. For the most severe wind events, standard reinforcement simply isn't enough to guarantee human survival. This is where FEMA P361 certified safe rooms come in. They provide near-absolute protection from extreme wind and the deadly impacts of windborne debris. Whether they're constructed as large community shelters integrated into public schools or small residential refuges tucked into a home, these deeply fortified spaces save lives when high ground or evacuation routes are simply out of reach. They're essentially the ultimate physical barrier between human life and atmospheric chaos. Section 5. Economics of Resilience, the Financial Impact. Finally, we're going to pivot from the realm of structural engineering to the economic reality of adopting and enforcing these disaster-resistant standards. Let's anchor this section with an established clear fact from the National Institute of Building Sciences. Mitigation investments can save money and reduce losses. Building safely is not just about avoiding human tragedy, although that is paramount. It is a highly calculated, financially sound strategy for long-term municipal and national economics. When communities decide to invest in resilient engineering today, they're essentially buying down their future financial risk. Adopting and strictly enforcing modern global standards, specifically the International Building Code, or IBC, and the ASCE 7 minimum design loads, drastically reduces future disaster losses. These are highly technical documents that calculate the exact wind, seismic, and flood forces that engineers absolutely must design a building to resist. And the data proves it. Communities adopting the latest versions of these rigorous codes consistently suffer less structural damage, experience fewer business interruptions, and recover at a much, much faster rate after a catastrophic event. The mathematical reality behind resilience is irrefutable. The relatively small initial capital spent on engineering compliance and hazard mitigation upfront is vastly outweighed by the sheer scale of financial loss avoided during a catastrophe. By fortifying our structures, we avoid millions of dollars in structural damages, long-term business downtime, and costly community displacement. Simply put, structural resilience pays for itself many times over. It protects both local economies and the very taxpayers who fund the recovery efforts. Which leaves us with a critical thought to consider. Is your local infrastructure built to actually survive the hazards specific to your geography? We highly encourage you to investigate your local building codes and ask what modern global updates could protect your community before the next extreme event occurs. Our built environment is our first and most important line of defense. Thank you so much for joining us for this explainer on resilient infrastructure.